Welcome to the BSides Hardware Hacking Village Lab number 4. I'll be walking you through this lab. My name is Altbier, and this lab is related to the Learn CircuitPython using the Adafruit Trinket presentation. So let us get to it. What we're going to need for this lab is the board, the custom PCB board that was included in your kit. This one has the components from the Arduino class and labs 1 through 3, and that's fine because we'll use the same board to proceed with lab 4 and 5. So let me go through what it is we're going to build. So in lab 4, we're going to work on using the Adafruit Trinket to control LEDs. So we're going to build a circuit for this using a tactile switch and an LED and some wires and resistors. And then we're going to write 4 pieces of code that are going to work with that circuit. Let's take a look at the circuit. So here we have the Adafruit Trinket M0 on a schematic, and we have all the pins documented here. And what we're going to do is on pin D4, that's digital 4, we're going to connect up a 100 ohm resistor and a 5 millimeter LED, and then we're going to bring that to ground. And then on pin D3, we're going to connect up 1/2 of the button, that's the tactile switch, and then the other half of the button is going to connect to the 3v3 port, that's the 3.3 volt voltage output port on the Trinket. Now, in addition to that, on D3, we're also going to connect in a 10,000 ohm resistor and bring it to ground. And this is called a pull-down resistor. This is going to ensure that pin D3 is always at a low voltage state unless we push the button, which brings it high. Because natural things in the environment, if they're not brought to ground, it can sense capacitance in the air and produce false positive signals. So we want to make sure we bring it down to ground using that 10K ohm resistor. So that's all there is to this circuit. One thing I'll note on the schematic, my previous schematics actually drew out all the lines. But that can become very cumbersome when working with schematics, especially if you have to cross lines over other lines. So I used this as an example of how to use labels in schematics to indicate 2 things that are connected together. So the 3.3 volt here is connected in both places. You can imagine a line going from here to here. That'd be the wire connecting it. Same thing with the ground. All 3 of these are connected to that ground label. So this allows us to make the diagram a little cleaner, but still portray what's connected to what. Okay, the physical layout. So like I said, we're going to work with the same board that we did for the Arduino labs. So it's going to have some things already connected to it, but that strip board has plenty of room on it that we're going to use it for the Trinket as well. So what we're going to do is we're going to connect up our Trinket female header pins and the LED and its 100 ohm resistor, the button and its connection to the 3 volts and its connection over to the digital in pin with its 10K resistor. The strip board connectors are all listed out here, and we'll walk through those as we put it together. So let me show you the components. Okay, so here we have the strip board. I'm actually going to move our Trinket out of the way, so we should have a Trinket ready to use on this when we're done putting it together. And then we have our LED, a 100 ohm resistor, our button, tactile switch, a 10K ohm resistor. We have 2 5-pin female header pins and some chunks of wire that I cut approximately to the size that I'm going to need to use them. Oops, and I forgot a piece of wire that I'll cut off in a second. And that is where we're going to start. Okay, so the first thing that I'm going to do is get my soldering iron going, get these components out of the way, and we're going to work with the headers. So we're going to put those header pins on. Okay, so once my iron is hot, I'm going to tin the tip. It's not quite hot enough. We'll give it just a second. And while we're doing that, I'm going to put these in. So these are going into connections 17 through 21 and J 17 through 21. So they are a little bit closer together than the header pins that we used for the Arduino. And I'm going to use some male header pins to hold them into place. That way they stay at a nice 45-degree angle on the board. And we'll flip that over and we can see those connections are ready to be soldered. It is a little wobbly with this configuration. So we're going to have to be careful as we apply pressure. Let's see if this is hot enough to take some tin. And it is. Okay, good. All right, so now we will solder our header pins on here. And this will allow us to connect up our trinket, but not keep it permanently on this board. We can take it off and use it for other projects in the future. The first thing I usually do is I get the four corners of the header. This way I know it's nice and set in that 90-degree angle, and I can pop those male header pins off of there, which is what's making it awkward. Alright, so I got those four pins done, and I'll pop these out. And we can see that stays nice and 90 degrees while we do the other 6 pins. There, and that looks really good. So we have some nice solder joints on there. That'll work. All right, so next we're going to want to add in our resistor and LED. So the resistor that I'm talking about is the 100 ohm resistor. That's going to drive the LED. And we're going to plug that resistor into D19 and H19. So if we look at the letters and the numbers, we can follow along and say D19 is up here and H19 is right next to the board. Right next to the header pin, rather. And it'll drop in like that. I'm going to open up the legs a little bit. And then at the same time, I'm going to work on my LED. So the LED is going to go into C19 and B19, but the anode is what we're going to put into the C position. The anode is the longer pin. The side with the short pin, and it has a little flat notch in the plastic, that is the cathode. So we want that going away from the power and towards the ground. Now you notice it dropped all the way in there on me, and we don't want it all the way down there. We want to keep it above the board. That way, as I heat this thing up with my solder, I'm not melting that yellow plastic. Okay, now what I'm going to have to do, because that LED wants to stick out like that, I'm going to have to find a position like this maybe, that I can hold the board to where the LED is not being pushed back up through the holes. And then we will solder it into place. Alright, and so we have some good solder joints there. See, the solder went all the way through. Our LED did drop a little bit, but it is still up above the board, so that's fine. And we're going to cut the excess pins off of here, that way they don't get in our way. Actually, on this LED, I'm just going to use my pliers to try to see if I can't push it down a little further, get it further away from the board. Because that'll bug me if it's not consistent with the other LEDs on the board. Let's see if that did anything. Yeah, I got one side. Try the other real quick. Try to get something under this. That's better. It's at least a little bit higher. Alright, let's cut our pins off and get to work on the rest of the components. Okay, so what we need to do now is bring this around to ground. Now, when we were working with the Arduino, I decided just for simplicity to bring all of the wires directly to the ground pin on the Arduino. But we don't have to do this on the strip board. We have a power rail. And what I'm going to do, the power rail is made up of two sides, a positive and a negative. The positive is called VSS, and the negative is called VCC. I'm going to use the VCC, that's my voltage common rail, and I'm going to use that to bring the ground in. So what we want to do is bring the cathode side of this LED over to the VCC rail. So we're going to take this short little wire, and we're going to strip the ends of it, and plug it into the A19 and then the VCC rail portion of 19 that doesn't have a letter, it's just called VCC. And I'm trying to be careful not to cut the wire, to only cut the plastic. That's why it takes it a little while to work through. And this is quite a small wire, so that increases the difficulty in working with it. And then take a plier and bend these down. What we should have is a little U-shaped wire like that. Need to bend it a little to get it in. When I'm working with these wires, it's usually trial and error to get the length just right to where it fits. But as we can see, I got it bent and it fits in there good. And so now I'm just going to solder those connections up. That popped up a little on me, so I'm going to push it down while I'm heating it up. There we go. Okay, so now to complete the circuit, to bring it to ground, we have to put in the other wire. And that other wire is going to go from E18 to VCC 18. E18 is this, let's see if I can point it out. It is this next row down, and it's this place right here. And what that's going to do, this pin on the trinket is the ground pin. So I'm going to be connecting from that ground pin over to the VCC. That'll connect ground from the trinket to the VCC. And so for that one, I'm going to be using a little bit longer wire, about that long. And we'll trim the ends of this one and get it in place just like we did the other wire. All right, and we will get it into place. Wants to fall out, so I'm just going to kind of bend those wires a little bit. And now let's solder it up. Okay. This one's looking a little bulby. Trying to get it hot. There we go. Got the pad hot. All right. So that one's done. So that takes care of our LED. So now we have a button to deal with. So this switch, I'm going to show it on the diagram real quick. So this is a single pole, single throw switch. So it has one little switch in there. But it has 4 legs, so they're interconnected. So A and B are interconnected, and C and D are interconnected. And you'll notice that the legs that are on the same side of the switch are of 2 different halves of the button, where the pins that are on opposite sides of the switch are the ones that are interconnected. So we'll use that in orienting how we're going to plug this pin in. So we're going to use N14 and 16 and Q14 and 16 as our connection places. Okay, and so here is our switch. Looks just like the diagram. And we're going to get it into place in N and Q, 14 and 16. These are a little tricky to get in because the legs like to fold. So you might have to finagle it to get it to go in. But you will notice that if you're going to connect it between N and Q, because of the distance involved, you can only put it in the correct way. It's not going to let you put it the other way because then it's not going to reach at all. This is the only way that the legs reach. And so then we have it connected as far as pushed down in there as far as we can get it. Try to get it even. And then what I'm going to do is lay the button onto the edge of my tool so that as I apply pressure to the button, it keeps the pins poking through while I'm soldering it. And we're going to solder that into place. And technically I only needed 2 of these pins, one on either side of the switch, but I'm soldering in all 4 positions so that it holds it in place, because the solder is not just for electrical connectivity, it's our mechanical glue. And there we go, so that's in there nice. Now you may notice that the button is sharing one of the Arduino pins, and that's not to worry about. This won't affect the Arduino at all when the Arduino is plugged in, and we cannot have both plugged in at the same time. It's just not physically possible because they both overhang. So yeah, this is not going to get in your way, and it was just wasted real estate that I'm using. All right, so then next we have to wire that button into power. And that pin is going to go from the R16 pin here, and we're going to bring it down to where that 3-volt connection on the Trinket is, which that's going to be N21. So if we look at this, N21. So it's that last row there. And so we're going to use a red wire for that, since that's a positive 3 volts. And looking at this wire, it might be a little long. We might have to trim it up, but let's get it one end done and then we'll take a look. So if I put that there, and then I come around, Yeah, I got a bit too much wire there. Okay, we'll trim this other end, and then we'll plug it in and solder it in. And I promise I will get to CircuitPython code, since that is what this class is about. But it's also about hardware development, so we want to make sure we know how to play with circuits. Alright, so we have N21 and we have R16. And just bend these wires out a little bit, that way they stay in place, and let's get it soldered. Okay, those look good. So we have that wire in place. And now we have to bring our signal wire down. So our signal wire is going to be this white guy. You can choose any color you like. I just chose white so that would be different and be able to be differentiated. And we're going to bring it from here over to here. So basically this wire is going from M14, M will be right here. 14 is going to be right that hole there. We're going to bring it from that hole, and we need to bring it over to H20, which H is this row over here, and 20 is there. So it's going to go right next to where that resistor plugged in. So the easiest way for me to do this, I could bring it on the back, and that would probably be the easiest way, but I like keeping the back free of wires for just solder points. So I'm going to use this gap between the header pins and solder it in between there. So we'll have to move it as we go and size it as we go. I'm not sure if this is too long. I'm pretty sure it's long enough, but I don't know if it's too long. But we'll see, and we'll trim as needed. Alright, so we'll bend an end down. Okay, and so we know it's going to go right here. That is M14. And I know I'm going to have to bend it right about there. So I'll make a nice 90-degree bend. And then when I put it back there, I can see I didn't bend it well enough. So let's try that again. Alright, so that's going to go through here, and then it looks like I'm going to bend it right here. And then, yeah, it's just a little too long because right there's my hole, and I need some wire to go into the hole, so I'll just trim off a little excess. And so then this wire I will trim. And we will bend it down. And so now we have our piece of wire ready to go. So let's plug it in place and see if it fits like a glove. Needs a little help getting in there, but there we go. And that looks good. So now we just have to solder the connections in place, and then we'll move on to our other resistor. All right. That's stuck up a little bit, but that's fine. Okay, so then what I'm going to do, I'm going to trim some of these wires down because they're getting to the point where they're starting to stab when I flip it over. You'll notice I'm covering the wire when I'm cutting it because those little chunks of wire can fly off of this cutter and we don't want them flying in our face. That's just a little precaution. Alright, that looks good enough. Alright, so now we have our 10K ohm resistor. And so this, we're going to put that between E20 and B20. So E20 is right here. It's the same row that we just put that wire in. It's the same strip, just the other end. And then B20 is right there next to our LED, just one row down. Because it's close to that LED, I'm going to use the pliers to pull its legs down. Alright, and then we'll solder him into place. My solder keeps bending out of my way. Let's try that again. There we go. And we'll trim our legs off. And just have one thing left, a little tiny piece of wire that is going to bring that 10K resistor to the VCC ground. So we will trim that up and connect it over. It looks like one of those pieces of metal stabbed me. It does not want to go in its holes, but we will make it. Sometimes wire just be like that. There we go. So it's in. Let's solder it up. All right. Just trim off a little of that. And there we have our completed circuit. So we got our LED, we have our button, we have our 10K pull-down resistor. All right. Okay, so I've plugged my Trinket in with the USB facing towards the top of the board. I'm going to use my USB safety USB connector to plug the Trinket into my PC, and that's going to have it open up a drive that is called CircuitPy. And that CircuitPy drive is where our code is going to be, and that is where we're going to modify the main PY file. So this code that we're going to put on here, we're going to just really test the board. This is the same code that I use for testing after a firmware upgrade. So we're going to walk through this code, but it's very simplistic. So the first 3 lines of code are just loading the libraries that it's using. It's importing board, which board has all of our definitions for our pins. It's importing digital I/O, which is for digital inputs and outputs to pins. And it's importing time, which we're going to use to pause things to make them go to sleep for a while. Then it's going to, we're going to assign an object called RLED. This is the red LED that's built onto the Trinket. We're going to assign that object a digital I/O feature called digital in/out, and assign it to board pin D13, and that's the digital 13 that is corresponds with the onboard LED. Because this is an input or an output pin, we have to specify direction. So we're going to say RLED direction is equal to direction output. And then we'll do a while loop. A while loop is a conditional loop, so we can set a condition on when it's going to run this. And our condition is just true, which means it's just going to run this forever. We're going to print a serial output called hello CircuitPython. We're going to set the value of RLED with RLED.value equals to true. Now with a digital output, we really only have 2 choices of what signals we can send. We can send true or false, which corresponds with 1 or 0. It's digital, so it's either a 1 or it's a 0. So if I'm sending a true, that means I'm sending 1, a digital 1, to the value, which is going to turn that LED on. And then I'm going to go to sleep for a second. Pause the loop there. That way we can actually see the LEDs on, because these loops can go very quicker than the human eye could catch it. So we want to pause it, that way we can see the LED. Then we're going to set the LED state to off with the false, and we're going to go to sleep again. So this is a very simple program, and the way I'm going to apply this is I'm going to run this editor called Moo, which I went into or mu, however you pronounce that. I went into this earlier in the presentation, and this is going to allow us to see what is running on this board and to put new code on there. Now, it just so happens, because I was resetting this board recently, this is running the code that we want it to run, as we can see here. And this is actually the code that is on the CircuitPy drive, the main PY file. It doesn't need any external library files. All of these libraries are built into CircuitPython. Let us actually take a look at this. So I have it, if you can see on the left side of the screen, you can see that it's blinking the onboard red LED. And now we're going to open up the serial monitor, which I can do just by clicking serial here. And we can see it say, hello, CircuitPython. Now, if I didn't have this mu program and I didn't want to install that, that's fine. I could still work directly with the code and open it up on Windows Explorer or some other way to get to that CircuitPy drive, edit the main PY file, and it'll work. Now, if I wanted to go with a serial monitor, I would have to figure out what COM port my device is using. In my case, it's COM9. And then I would open up a terminal programs like PuTTY or some other terminal program and have it connect to COM9. And I would see the serial output that way. So this is handy for this presentation because it's all in one tool, but you don't have to use this. All right, so we see that that's working fine. So now let's go to our next section of code, which will be a little more complex. Okay, so what we're going to do for this next section of code is we're going to light up both an external LED and the onboard LED, and we're going to turn it on and off at the same time so that it'll light both of them. And this is kind of hard to see. Let me see if I can open up this code in my normal code editor and share that so I can walk through it there. Yeah, that's a little better. Yeah, so what this code is going to do, just like the last code, we're going to import board, digital I/O, and time because we're using functions out of each of those. We're going to assign our LED value to a digital in/out on D13. Then we're going to assign this LED that we just soldered onto the board, which I'm calling LED4 because that corresponds with the schematic. I'm assigning it to a digital in and out connector on pin board.D4. So that's digital 4. And then we're going to set the direction of these pins. We're going to set them both to digital output pins. And then I'm going to do a while true, which is going to be my main program loop. Then the first value that I'm going to set is to set the LED state to on. Now I'm setting both LED values at the same time, just using 2 equals. We can have as many of these as we want if we want to set different objects or variables to the same value. We can just chain them like this. So we're setting our red LED and then LED4 both equal to true. And then I'm going to print the serial output of this, which that kind of line wrap. Let me close that down. There we go. Now, in our previous example where we printed output, we just showed output that was text. In this case, we have not only a string, which is like text, but we have the actual values from our objects, our variables. And we can do this all on one line, print line, by doing comma spaces between our different types. So I have a string with a comma followed by a variable and a comma and a string and a comma, and it'll print all of these together. And then I'm going to pause, and then I'm going to do the same thing to turn the LEDs off and print that they're off. So this is the code that we want to load up into our device right now. And you can see the device on the top left of my screen. Let me drag it down a little bit more so that you can see it better. And I'm going to open up that move program again. And in that, I'm going to paste this code. So I'm just going to select everything that's there and delete, and then paste all the stuff that I just copied. And we can see it has all of the stuff from my other editor. And I'm going to click Save. And we see it applied the change. It gave us a nice status message when it applied the change. And we can see that it's setting the two values true and false and true and false. And it's hard to see the color there, but it is lighting up both LEDs. Just a little dark. Let me see if I can get the lighting fixed on that. There we go. That looks a little better. A little dark in the corner makes it light up bright. So we can see our LED is lighting at the same time as the onboard LED. And our code is running fine. So now let's look at our next piece of code. So for our next piece of code, what we're going to do is turn this on-off blinking light that we have into something that's going to fade on and off using pulse width modulation, or PWM, that's built into the digital pin we're using. So the digital pin is going to mimic an analog output, where analog outputs will start off and provide low voltage and slowly get up to high voltage and then come back down to low voltage in an arc. Digital is usually just on or off, on or off. And what pulse width modulation does is it pulses the signals of on, off so many times in a short period of time, like so many times a second. And the amount of times that it pulses on versus off will determine how the LED is set. So the way this works is the pulse width modulation uses a duty cycle, which is that number of times it's going to pulse high or high voltage versus low or no voltage. That duty cycle, the number of times it's going to pulse high, determines how much power it's mimicking in an analog sense. And the duty cycle uses a 16-bit number. So that would be from 0 to 65535. 0 being completely off, 65535 meaning completely on, or it's 100% of the time pulsing that signal. So let me step through the code to show you what we got, but first I'm going to do that from my code editor because that is a little more clear there. And this is the old code. I'll pull up the new one. Okay, so the first thing that you're going to notice is that we're not using the digital I/O anymore. Instead, we're still pulling in board and time, but we're pulling in the pulse I/O library. This is still another built-in library, so we don't need any special files for it. We're going to assign the LAB04 object to a pulse I/O PWM out pin using D4. Now, because this is an output-only pin, we don't need to specify a direction on this one. And then in our while loop, we're going to use a couple of for loops. So I said before, a while loop is a conditional loop, which we're using a condition of true, so it's always going to run. Well, in these for loops are iterative, meaning it's going to run it a number of times. It's not waiting on a condition other than the number of times. And I'm going to give it a range of 100, which this range means it's going to go from 0 to 100. And then we're going to run it again, going backwards, so that it starts at 100 and goes down by 1 each time until it gets to 0. So this way we can like fade the LED on from 0% on to 100% on, and then fade it off from 100% down to 0. Now the way that we're going to do this fade is using these pulses. So we're going to set the LED duty cycle. So you'll notice this is different than when we set the LED before and we were using value. We're not just setting it a digital value, we're setting it a duty cycle, which is that number from 0 to 65535. And what we're going to send it, we're doing a little bit of math here to get that percentage. So basically I is going to be, in this for loop, it's going to be a number from 0 to 100, right? So if I is 50, let's say, I'm going to divide it by 100, and that gives me 0.5. And I'm going to take 0.5 times it by 65535, and that gives me half of that number, some 32,000, whatever. And it does that all through this cycle. So basically it's just turning I into a percentage that we're timesing by the maximum. And so with that, we're setting how many cycles in a second the LED is going to receive a high voltage versus a low voltage. And that'll be its percentage of onness, its brightness, if you will. We're going to print what that value is, and we'll sleep for a very short period of time, like 100th of a second, because we're going to loop through this 100 times. So setting it to 100th of a second means this whole fading up should take about a second. Now in our second for loop, we're doing the same thing, it's just the range is different. So we're counting from 100 down to 0. But all of this is exactly the same. So we're using that same math to turn I into a percentage that we multiply against the duty cycle maximum. We're going to print it. We're going to wait. So let's copy this code to our board and see how it looks. So let me launch that move program again. Okay. And I'm going to select all the code that's there and replace it with my new code. And we will just double check this real quick to make sure the copy and paste was okay, but there's not a whole lot here. So yeah, this looks good. So now what we're going to do is save it. And we should, when I click save, you should see this on-off LED start to fade on and off. And there we go. So you see how it's now fading on and off with us. Now let's take a look at the serial monitor. And we can see it's posting one of these every 100th of a second, so it's really blasting the serial out. But we can see it counting up and down as far as those duty cycle values. And that's allowing it to fade on and off. And so that's how pulse width modulation, or PWM pins, work in CircuitPython and with the Trinket. All right, let's go to our next section of code. All right, for our next section of code, what we're going to do is we're going to turn LEDs on and off using a tactile switch. That's the button that we soldered onto this board. So this section of code is going to read the state of the button and use that to control the LEDs when it's pressed. I'm going to use the button in two different ways, as a conditional check and just as a value that we can set. And we're going to take a look at that code. Let me pull that up in my editor where it's a little more clear. Okay, so for this code, I'm going to use board and digital I/O and time libraries. And this first section is just like we've been doing. We're going to set the red LED and the external LED as digital outs. And this time we're going to add in the switch. So we have switch is going to be on D3. And then we're going to set the directions of these pins. So the LEDs are both going to be outputs, and the switch is going to be an input. And then we're going to start our while loop for the main loop. We're going to read our button into a variable, or we're going to read our switch value into a variable called button. We're then going to print that value out to our serial output. Then we're going to use a conditional loop, a conditional statement, an if statement, to find out if the button is equal to true. That means if it's pressed, because this is a digital input, it's only going to give us true or false, 1 or 0, right? So if I press the button, I should get true. And if that's the case, I'm going to light up the red LED, just the red one. If not, then we use else. Then I'm going to make sure the red one stays false. Now for the external LED, I'm going to work this a little bit differently because we know the button variable is getting its value from a digital input. It's either going to be true or false. So I'm actually going to use it as a value and set the external LED value for LED4 value, to whatever the button value is, which should be the same true false that red is. And then I'm going to put it to sleep for about 1/5 of a second. This way, when it's looping through, it can be going fast enough to register my button pushes. And that's all there is to this, but I wanted to definitely call out the 2 different ways of working with this data. So when you're taking values in from an input, you can use it in any kind of a loop or a conditional statement, but you can also just set it as a value. Now in this case, the digital input its value is limited to 1 or 0. From an analog input, you would get whatever the value is on the analog pin that it's receiving. But you could still use that, assign it, and use it. So let's go ahead and copy this code, and we will open up the Mu editor. And we will paste our code. And we'll save it, and when I hit save, we should see changes on the board that's on the upper left-hand side of the screen. And what we see is the only light that's lit right now is the center green RGB LED. And that light, when it's lit solid, means it's working. It loaded a code and it's running that code. And so now I can push the button and see what happens, and we see for as long as I hold the button down, it lights both LEDs, the external and the internal, even though I'm assigning them different ways. And if we look at our serial monitor, it's showing us what the button value is, and when I press that, it shows us it changes to true. All right, that brings us to the end of Lab 4. Thank you so much for working this lab with me, and I hope to see you on the next lab, Lab 5, which will continue working with CircuitPython and the Trinket. Thank you.